Good to go? All right. Good morning, everyone. My name is Frank Bosch. I'm a professor at Yale University, and the organizers asked me to tell you about the galaxy halo connection, which is a topic that I've been working on for, I guess, a good 2 decades now. So a long time. So here's my attempt to deliver. Let's see if this works. Yes. Okay, so the outline, I'm going to talk today and tomorrow morning. So today, since I'm the first speaker, and since I want to set things straight, that we all have common language, I'm going to start with a little primer on structure formation. That's probably going to take me most of the first 40 minutes or so till the break. And after that, I'm going to talk about the halo model. The halo model is sort of an analytical tool that was developed in the beginning of this millennium, and it really got this thing going of us thinking about modeling the galaxy halo connection. And then we're going to talk about halo connection modeling itself. I'm going to 3 different statistics that people use to do this, which are the halo occupation distribution, the conditional luminosity function, and subhalo abundance matching. And probably that's where we're going to end today. And then tomorrow, I'm going to talk about empirical constraints, okay, different methods that we use to constrain the galaxy halo connection, which include galaxy clustering. I'm going to focus on galaxy lensing, and I'm going to talk about satellite kinematics a little bit. Then we're going to talk about the actual constraints that we have obtained. What have we learned about the galaxy halo connection? Okay, that talks about the stellar mass halo mass relation. We're going to focus a little bit on the scatter in that relation, what we know about that, and what we know about how satellite galaxies are distributed. And then we're going to come to something that's, I think, of most interest to most of you, which is cosmology, the cosmological part, because a lot of this halo occupation modeling is done with regard to cosmology. We want to learn something about cosmology. And this brings up something that most of you may have heard of, which is the S8 tension. And then everything is good up to that point, and then we're going to talk about all the things that can go wrong. Okay, and that brings us to things like artificial disruption and assembly bias and baryon effects. Okay, that's where it gets really dark. All right, so a few preliminaries. I sincerely apologize for those of you whose work I'm unable to cite. This work has rapidly expanded, and there's many, many, many papers, and I'm unable to cite all of your work. So apologies for those who feel misrepresented or underrepresented. I hope I don't misrepresent anyone's work. It's my goal, at least. This review is also heavily biased, both in terms of my views and scope. So occasionally I will give my own personal views on things, and feel free to disagree with that, either in silence or by engaging in a discussion. It's probably too difficult to have everyone get involved in a discussion. But don't hesitate to raise your finger if you have a question or a comment to make. I also will focus more on topics that are more, that I'm more familiar with. So again, that also will limit the scope of what I'm going to talk about. This review is also a little bit more historical rather than up to date. And there's 2 reasons for that. First of all, the number of papers that are written in this field are exponentially increasing, and it's exponentially more difficult for me to keep up with the literature. But also because later in the afternoon, Lehman Garrison is going to tell you how to write an HOD code, halo occupation modeling code. And he's going to show you that, you go to Python and you say, import this, import that, and then plot this, and you're done, right? And I want to get you guys a feeling for, while you guys were still in the sandbox in kindergarten, some of us were in the trenches writing real code, Fortran and C, that made this all possible. And I want to give you guys a feeling for how this sort of developed over the years. Okay. And then finally, hopefully, this will spawn interest in this field, because like any other field, we need new young people with bright ideas to make progress in this field. And I already said this, that please do not hesitate if you have a question. If I say something, a terminology you've never heard of, and I don't explain it, just raise your hand or shout out, okay? I won't be able to see everyone, so. All right, let's get going. So as I said, I'm going to start with a primer on structure formation. And structure formation is basically the story that brings us from the initial conditions, okay, to all of the structure in the universe. We try to understand how that works. And the initial conditions, we sort of can read them off in the cosmic microwave background, where we see temperature fluctuations. Okay, these temperature fluctuations are about 1 part in 100,000. And they're due to similar fluctuations in the density field. And I want you to appreciate that 1 part in 100,000. Okay? That's tiny. You think of the surface of a ping pong ball, it's wickedly smooth, right? At least if you have a decent ping pong ball. But if you put it under a microscope, it has little irregularities, little dimples. And they're about 1 part in 10,000 for a decent ping pong ball. So that means that this cosmic microwave background field, okay, which represents the density field of the universe about 380,000 years after the Big Bang, was smoother than the surface of a ping pong ball. And yet all these tiny irregularities, those are all the seeds for structure formation. That's where all our halos and galaxies came from. Now, where did these tiny fluctuations come from? Well, we think it has something to do with inflation. We think that there were quantum fluctuations in a scalar field called the inflaton at early times that created these fluctuations. Okay, and that means that in that picture, our own Milky Way ultimately has its origin in a quantum fluctuation in some wacko scalar field about 10 to the minus 33 seconds after the Big Bang. Right? It's a fantastic story, but it seems to work. And these fluctuations, which we can see in the cosmic microwave background, they grow, and they grow very simply by gravity. Okay, and gravity says if I have an overdensity here, it's going to pull matter towards it. It's going to become more overdense. At too bad for the underdense region, which you're going to lose the matter, and it will become more underdense. It's like capitalism, right? The rich get richer, the poor get poorer. It's just here gravity is doing the work. Now the cool thing is that as long as these perturbations are small, okay, significantly smaller than unity, we can use a powerful tool called linear perturbation theory to exactly write down and describe what happens, how these perturbations grow over time. And at some point, these perturbations become of order unity, and then all the shit hits the fan, as they say in American, right? It becomes impossible to deal with this analytically. So what do? We run numerical simulations, and these numerical simulations, they're very good at treating the nonlinear physics. And what they show is that all these perturbations are going to collapse and they form dark matter halos. Okay. So let's start by trying to think about how can we quantify or characterize our density field in the universe, okay, of all the matter. And so that rho x density field. What we normally do is we work in terms of an overdensity field, delta of x, which is the density at a given location minus the average density divided by the average density. Okay? So if delta is positive, it means an overdensity. If it's negative, it's an underdensity. And we believe that these perturbations, as I said, are somehow created by a random process early on in the universe, probably related to quantum fluctuations. Okay? And that random process then created our density field. And what we want to do is we want to describe the probability function P delta. What is the probability that at a given location in the universe, I ended up with a certain value for delta? Okay? That statistically describes this random process. Now, what we want to do, what we can do is if you can ask, what is the expectation value for delta? That's asking this sort of brackets are basically what is defined as an ensemble average. Okay, suppose you go to a given location in the universe and you look at the early universe, you say, what is the value of delta that I find there? Well, it can be positive, can be negative, okay? It has a value that is described by this probability function. Now, if I were God and I would make a new universe, but based on the same random process, that same location would have a different value for delta. Okay? And if I would make a million universes like that, at each time I go to the same location in that universe, if you can speak of such a thing, right, then you would basically sample that probability function. And this ensemble average, what it basically means is, if I would do that a million times and I would go to the same location, what is the average value of delta that I would find there? Okay. And mathematically, it's given by this expression. It's just integrating over the probability function, okay, times delta. Now, of course, we only have one realization of the universe, our own, but there is something called the ergodic principle. And the ergodic principle says, well, this ensemble average is the same as a spatial average. And that's because if I go to that part of the universe there, the density field there is unrelated to the density field at that part of the universe there. And therefore, I can think of them as different realizations. So an ensemble average is the same as a spatial average, ergodic principle, okay? And if you do that, you integrate delta over the entire density, over the entire space, you of course get zero. That's from the virtue of the definition of delta. So not very interesting, but the second moment is more interesting. The second moment is just given by this expression here, delta squared, and that's what we call the variance or sigma is the variance of the density field. Okay, it describes what is the characteristic amplitude of these fluctuations, and that sigma will grow over time just due to that structure formation that I mentioned earlier. Now, you can also ask, well, what about the probability that at location x1 I have an overdensity delta 1, and at a location x2 I have an overdensity delta 2, where locations x1 and x2 are separated by a certain distance. Well, if these densities, these overdensities, different locations have nothing to do with each other, if they're independent of each other, then that probability is just going to be the probability, the product of the probabilities for delta 1 and delta 2. And therefore the expectation value for delta 1 times delta 2 is just going to be the product of the expectation value for delta 1 times that for delta 2, and that, since both are 0, that's going to be 0. Okay. So what I've just said in words is, if delta 1 and delta 1 are not related to each other, if they're uncorrelated, then the expectation value for their product is 0. Okay. It's a standard result in statistics. But are they uncorrelated? Well, hell no. First of all, the random process doesn't make them uncorrelated. But even if it would, there's something called gravity. And if I have an overdensity here, then location 2 knows about the fact that there's an overdensity because gravity is a long-range force. So there's no reason to expect these things to be uncorrelated. And that correlation in them, the actual value of this, that is what we call the two-point correlation function. It describes how the density field at location x is correlated with that at location x2. Okay. And it's a function of the distance between these 2 points. Okay. Note that it only depends on the distance and not on the direction of the distance. That's an assumption, that the universe is isotropic. There's no preferred direction. So it can only depend on the amplitude of the distance, not the direction. So that's a two-point correlation function for a continuous density field delta of x. You can also define the two-point correlation function for discrete distribution of points or particles, dark matter particles, galaxies, you name it. The way you do that is you say, well, 1 plus psi of r, the two-point correlation function, is the ratio between the number of pairs of particles separated by a distance r divided by the number of pairs that I would get if I take the same number of particles, but I distribute them randomly. Randomly means according to a Poisson process. And that means if I put down my nth point, it's independent of where I put down my previous n to the minus 1 points. That's a random Poisson process. So if you have a random distribution of particles, like I tried to make a random distribution of particles here, and I would compute the two-point correlation function, well, the number of pairs that I get is basically the same as the number I would get for a random distribution, because it is a random distribution. So this ratio is 1, and my correlation function should be about 0, with some fluctuations just due to the discreteness. But if the particles are clustered, what I have is I have a larger number of pairs with a small separation compared to random, and my correlation function will be positive on small scales. Now, importantly, the number of pairs, okay, when I make them clustered, is of course going to be conserved. The same number of particles, same number of pairs. So if I have a boost of the correlation function on small scales, it means on some scales the correlation function must be negative. Okay? You're probably not familiar with that. All the correlation function that you'll ever see about galaxies, they're always showing you a power law. Okay? But that's because all they're showing you is this region here in the inner part. If you would be able to measure the correlation function out to sufficiently large scales, you should see that at some point it becomes negative. Okay? So keep that in mind. So that's a two-point correlation function. Now, I talked about the 1 point statistic, the expectation value for delta. I talked about the second moment, okay, the variance. I talked about delta 1 times delta 2. That's this, the correlation function, the 2-point correlation function. How many of those things do I need to completely specify a density field? Well, in principle, I also need to define the 3-point correlation function. What is the probability to have delta 1 here and delta 2 there and delta 3 there? And the 4-point and the 5-point and the n-point. In principle, if I really want to quantify statistically the density field completely, I need moments to infinite order, which is annoying, but there's good news on the horizon. We have good reasons to believe that the density field that was created, and we actually have constraints on this, is what we call a Gaussian random field. Now, Gaussian random field, what it means mathematically is the following. It means that the probability to have delta 1 and delta 2 and all the way up to delta n, where n can be any number, is given by this expression. It looks complicated. If you look here, the main point you should remember from this is that if you look at it carefully, you see here's a covariance matrix, which is nothing but the inverse of the two-point correlation function. So what I'm writing down here is that this probability function for all n points only depends on the two-point correlation function. In other words, the two-point correlation function, this two-point statistic, completely describes, in a statistical sense, a density field. That's a characteristic of a Gaussian random field. It's super powerful. We don't need a 3-point. There's no additional information in the 3-point or the 4-point function. Done. Completely described it. Okay, so smiley face. Yeah. What we often do is we take this density field and we break it down in Fourier modes. Okay, standard thing you do in physics. We also do it for a density field. So we can think of this density field delta x as a sum of plane waves. Each plane wave having its own amplitude, okay, which is this delta k, it's the amplitude of that mode. It has a wavelength, okay, which is related to the wave number k, okay, and it has a direction. And if I just take a whole bunch of those things with different random phases and I add them together, I get a random field. And if the phases all are completely random, I get a Gaussian random field. Okay? That means I can write my density field, okay, just as a sum over plane waves. Delta k is the inverse of the Fourier transform of the density field. And now the cool thing is, I can define something here, the amplitude of the modes, delta k squared. What is the expectation value for the amplitude of these modes? And that is what we call the power spectrum. And the power spectrum, turns out, with a little bit of math, you can try this at home, it's very simple. You can show that the power spectrum is nothing but the Fourier transform of the two-point correlation function. Okay? So whether you want to work with the power spectrum or the two-point correlation function, it's identical. Okay, just depends on what you prefer, whether you might like to think of Fourier space or normal space. But that's it. So when I say a Gaussian random field is completely specified by the two-point correlation function, it's equivalent for me to say completely specified by the power spectrum. Okay. All right. So now how does the density field evolve? That's what we are interested in. We want to do the dynamics. We want to do structure formation. Well, it turns out that as long as this density field, delta, is small, the fluctuations are small, we can use linear perturbation theory. And basically what it means, what you do is you go to the fluid equations, the continuity equation, Euler equations, you use the Poisson equation, which relates the density to the potential, and you perturb them. And then you linearize these perturbed equations, and you do a little bit of math, okay, which any decent book on cosmology will tell you how to do it, and out pops this equation. Okay. Now I've done this in Fourier space here. And what this says, this is the evolution, the time evolution of the amplitude of the mode with wave number k. How does it evolve? Well, let's look at the different terms. Okay. Here's the first term. There's an a dot over a there. A is the scale factor of the universe. Okay. A dot is how fast does the scale factor change as a function of time. How does the universe expand? That's given by the Friedmann equations. I hope you're familiar with that. A dot over A is the Hubble parameter. So what is that doing there? Well, okay, what it's telling you, this is called the Hubble drag term, because you have a perturbation, you have an overdensity. That overdensity wants to pull matter towards itself and become more overdense. But at the same time, the universe is expanding. Okay, and that sort of goes in the opposite direction to growth. So that's called the Hubble drag term, and it resists growth. It goes opposite to growth. The next term that we see here has a G in it. So ta-da, it's probably related to gravity. Okay, and indeed, that's the term that tells you, okay, these perturbations want to grow due to gravity. But in addition to Hubble drag, which resists the growth, there's something else. The next two terms are similar. There's a CS squared, there's a sound speed. And here's a temperature and entropy, and all that stuff tells you something about pressure. Okay, these are pressure terms. And note that there are minus signs there because pressure opposes growth. Okay? So these perturbations want to grow, but if there's pressure, the pressure pushes back. So gravity likes the perturbations to grow. There's two things that are opposing growth, pressure and Hubble drag. And that's basically what this equation expresses. The cool thing is, it's quite straightforward to solve this equation. Okay? And therefore we can in linear theory, we can describe how these perturbations evolve as a function of time. The other thing to notice is that, look, I wrote down an expression for how the amplitude of this mode evolves. And only thing that appears is K. None of the other Ks of the other modes come in there. That means each mode evolves completely independently from the other modes. That is the key of linear theory. That's what linear means. Okay, so these modes, you can do this mode by mode, and that's why this is often done in Fourier space. Each mode evolves independently of the other modes, and the evolution is described by this simple equation. And what it means in the end is we can describe now immediately how my power spectrum evolves as a function of time. So here it is. The power spectrum as a function of time is related to the initial power spectrum. Well, what's the initial power spectrum? Well, we think that has something to do with inflation that creates these perturbations. And we actually have very, very good constraints on it from the cosmic microwave background. We know it's basically a power law with a slope, pk is proportional to k to the power n, and n is very close to 1. If it's 1, it's called the Harrison-Zeldovich spectrum. You may have heard of that. But we now have constraints. It's like 0.96 something, I forget. And that's exactly what inflation predicted. And it should be close to 1, but probably a little bit lower. So we know what the initial power spectrum is. And then there is something called the transfer function, T of k. That's a complicated thing. I think that Jill will talk more about that. What it basically describes is what happens to these perturbations during basically up to the point of recombination, up to basically the time when the CMB is created, 380,000 years after the Big Bang. And what happens during that period has scale dependence in it, and that's why this has a k dependence. That's a transfer function. I'll say a few more words about the transfer function. Basically, the transfer function, that's where the dependence on the nature of dark matter comes in. If you have warm dark matter or cold dark matter, the transfer function will be different. Okay? So that's where that comes in. And then finally, there is this d of t term, which is a linear growth rate. That d of t is basically the solution to this equation. It tells you how the perturbations are growing in the linear regime. And note, there's no k dependence because it doesn't depend on k. It's the same for every k. All modes grow in the same rate. Okay. The only k dependence that is introduced in the early part of the universe, and that's described by the transfer function. So this is it. This describes the linear evolution of the power spectrum, and we can work out all these terms. D of t, by the way, has a cosmology dependence. That depends on omega matter, sigma 8, no, not sigma 8, omega matter, Hubble parameter, that sort of stuff. Okay. So here's a visual representation of this. So here's power spectrum as a function of k. So large k means small scales. Large k is small scales. That's what I said. Here's the initial power spectrum. It's just a power law with a slope almost 1. Now, if you look at the power spectrum shortly after recombination, what it looks like is given by the solid line. Okay? And it has undergone this sort of bending. And that is what is described by the transfer function. The transfer function describes what happened there. And basically what happened there, most of this effect is due to something called the Mazaros effect or stagnation. Basically what happens if you have a small perturbation, okay, small wavelength, and it enters the horizon early, when the universe is still in a radiation-dominated regime. And when the universe is in the radiation-dominated regime, the universe is expanding a bit faster than during the matter-dominated regime. So the Hubble drag is large. So these perturbations enter, they go like, ha! They finally realize they're a perturbation because they're now causally within the horizon. They go like, ah, I'm an overdensity, I want to collapse. No, the Hubble drag prevents it, and it's stagnated, it can't grow. Okay? Things outside the horizon magically can grow. Okay? And so what happens is if you have a very small perturbation, it comes into the horizon very early, it experiences stagnation for a long period of time. A perturbation that enters just before equality has just a very short period of stagnation. Okay? And therefore the small perturbation experiences more stagnation for a longer period of time, and therefore its power is more suppressed. Okay? And this turnover is exactly the horizon at matter radiation equality. Perturbations on this side, they enter the horizon after the universe has already become matter dominated. They come in, they don't have this stagnation effect, they immediately can start to grow. Okay, so that's basically where that comes from, and that's described by the transfer function. Transfer function also describes things like free streaming. Okay, for the dark matter particles. That's why if you have warm dark matter, for example, the power spectrum will turn over here. It will be cut off. Those are all effects that I don't have time to go and describe. It also describes acoustic oscillations for the baryons. Baryon acoustic oscillations, you may have heard of that. That is also described by the transfer function. So all that physics, okay, is described by the transfer function. And you can just download all sorts of tools nowadays to just compute the transfer function for any cosmology. All right. Let's see. Right. So here now is a pictorial view of how perturbations grow over time. It's a complicated diagram, but what I'm plotting here is the evolution of a mode with a wavelength that roughly gives rise to something like a Milky Way at the present day. Okay. So the gray area is the time when the thing is outside of the horizon. This perturbation here is growing, comes inside the horizon, and this is matter radiation equality. By the way, this is the x-axis, this is a scale factor. So 0 is the present day. Okay. This is about a redshift of 1, a redshift of 1,000. This is roughly the cosmic microwave background, decoupling. And at about 20, 30,000, we have equality, 40,000, forgot. Matter radiation equality here. Okay. So this one comes into the horizon. It's still in the radiation-dominated area. It has stagnation. And then it enters a matter-dominated area. It starts to grow. And it just grows according to that linear growth rate. And that continues to do. Okay. The baryonic part does the same thing, and then it undergoes this wiggle because it has pressure and it starts to sort of have oscillations. Okay. And then there's something called silk damping that kills the perturbations in the baryons, but then afterwards the baryons see the dark matter and fall back in. And so, this entire escapade here, has zero net effect, except for some small interesting physics I don't want to go into. The upshot being all this stuff here, what happens here, that is what is described by the transfer function. After that, it's super simple up to the point when things go nonlinear. But this part here, that is just every mode just grows according to the linear growth rate, d of t. Ta-da! And then at some point, these density perturbations here start to become of order unity. And then a lot of stuff happens. But first, let me tell you what happens to this probability distribution, P of delta. Okay. So it's a Gaussian. And initially, okay, the variance is very, very small. Okay. The variance is about 10 to the minus 5, just about the time of recombination. And what happens over time is the distribution is broader. The overdensities become more overdense, the underdensities become more underdense. The evolution of each delta is just given by this d of t. So it continues, and it continues. Okay, the variance in the density field increases over time according to the linear growth rate. Note that I've bounded it here by -1 because delta cannot be less than -1. Just look at the definition of delta. If delta was less than -1, it would mean that the density would be negative. Okay, as far as I remember, that's not allowed. Right? So it can't go past -1. And if it goes above +1, if it's outside of that range, then we're no longer in the linear regime. So as long as we're in the linear regime, like here, we're good, and we can describe the growth by the linear growth rate. Now, at some point, some parts here are going to stick above +1, and these things are going to go nonlinear. And then everything else breaks down. We can no longer use linear perturbation theory, no longer valid. Darn. These modes start to couple. Up to that point, all modes evolve independently. Nice, simple. Now they start talking to each other. That becomes a ginormous mess. People try, very brave people try to do this analytically with high order perturbation theory. Huge disaster. Well, no, it's great, but mathematically it's a disaster, at least for me. So the other thing that happens is non-Gaussianities develop. Why is that? Well, on the positive side, the perturbations can go larger than +1, but on the negative side, they can't go more negative than -1. So this thing starts to get skewed. And it's no longer Gaussian. And that means it's no longer sufficient to describe the density field by a power spectrum or a 2-point correlation function. No, I now need to include the 3-point and the 4-point and the n-point if I want to completely specify the density field. Okay. So this Gaussian, this aspect that the two-point correlation function describes everything completely is only true up to the moment that things go nonlinear. And it goes nonlinear, everything goes down the window. And basically, we use embodied simulations, and these show that this thing sort of at some point it goes collapse, and then all sorts of stuff happens, virialization, violent relaxation, and the outcome is somehow a dark matter halo. Okay? And we use embodied simulations to follow that process. So in terms of our power spectrum, what happens is, well, we had a linear power spectrum, but over time, what's going to happen is, at some point, these small modes, these small K modes go nonlinear first, and they start to collapse. And I get a boost of my power on small scales. And over time, smaller and smaller structures start to collapse, and this nonlinear transition happens at smaller and smaller K, at larger and larger scales. Okay? And you need embodied simulations to basically work out what this thing is. Although, that's where the halo model comes in, as we'll see later on. The halo model can do this analytically. All right. So typically we use embodied simulations, they show us basically that what happens is you form halos. So you go to your embodied simulation, dark matter only, no baryons for now, please. Okay. Baryons make everything complicated. Dark matter, nice. Gravity. Collapse, halos form. You go into your simulation and you just go and count halos. You find halos, you run a halo finder, and you ask how massive is my halo, and you count your halos as a function of mass. Okay? How many halos per co-moving volume as a function of mass? Here's the number. That's basically called the halo mass function. Okay? Now in red are the results from a simulation. Okay? And what you see is that over time, you get more and more halos, and the maximum this is sort of what we call a Schechter function, right? So it has a power law at the low mass end, and then at some point an exponential turnover at the massive end. And over time, what happens, especially late times, you see there's very little evolution at the low mass end. Basically, you add more and more halos at the massive end. Okay? And that's part of that hierarchical formation. You form your low mass halos first, they merge together and build bigger and bigger and bigger halos. Okay? So when there's no evolution here, it doesn't mean that those halos are not evolving. They are evolving. A halo here at redshift 4 ends up in a halo that's much more massive. Okay? They merge together and make a bigger halo. But what happens is the rate at which these halos are depleted by being accreted into halos is sort of the same as the rate at which new halos come into existence at that mass scale. And there's a nice equilibrium sort of here. But at the massive end, you continue to build bigger and bigger structures. Okay, so we can use the simulations to do this. Now, in 1974, President Schechter had a great idea. He said, oh, can't we just predict what that halo mass function is? And basically the way that they did it was say, well, you know, okay, I'm not allowed to take my linear theory and make it go into the nonlinear regime, but screw that, I'm going to do it anyways. I'm going to just continue to make my distribution, describe it by Gaussian, even though this is completely unphysical, I don't care, I'm just going to continue doing that. And they calculated, or it was calculated, it was known that if you take a spherical perturbation in the universe, okay, initially it's expanding with the universe, okay, so the density is going down, but the overdensity with respect to the background is going up because it's expanding a little bit less rapidly because matter is flowing in. So this overdensity gets larger and larger and larger. At some point, it becomes order unity, and it says, to hell with this expansion. I'm massive enough. I'm going to collapse under my own weight. It's going to turn around, boom, and collapse into a halo. And you can calculate when does that happen? When does that turnaround and collapse happen? And it happens when the overdensity reaches a critical value of 1.686. Every cosmologist knows that number from now on. 1.686. That's where collapse happens. So President Schechter said, okay, I'll just take my Gaussian and I can calculate at any moment in time what fraction of the mass lies above delta crit. And I'm going to assume that that fraction of the mass in the universe has collapsed and formed halos. And all I now got to do is figure out how is that mass distributed over halos of different masses. And President Schechter said, I'm going to do that by taking the density field and smoothing it. Taking a smoothed version of the density field, smooth it with kernels of different sizes, of different masses. And by looking at the statistics of these smoother density fields and always asking that question, they were able to devise a scheme to figure out the halo mass function. Very nifty. You should not believe that it works, because you're violating all sorts of weird things here, right? But hey, you can write it down and see how does it work compared to the simulations. Okay? Now, I should point out that in 1991, Dick Bonterel wrote a fantastic paper where they said, this project is all nice, but we can do a little bit better. We can do a little bit more, to satisfy the mathematicians. We can do a little bit more sophisticated work, and they came up with something known as extended projector theory. And extended projector theory is based on something called the excursion set formalism. No time to discuss that. Just think it's a little bit more sophisticated than normal projector, and it gives the same results. But they were able to compute the mass function. If you do that, you use that projector, you get the dashed lines here. And look, it's not a perfect fit, but the shapes, the evolution with redshift looks pretty darn good for such a hokey theory. Okay, and then in 2000, Shet, Moe, and Torman said, well, we can actually even do a little bit better because we've assumed spherical collapse. I know every freaking overdensity is spherical. Okay, it's nice for a mathematician, but in reality, these things are ellipsoidal. And you can actually work out ellipsoidal collapse conditions in an expanding universe, and that modifies things a little bit. Everything else stays the same. They just said, okay, we go from the spherical collapse, this 1.686, we're going to change that, and we're going to use ellipsoidal collapse conditions and do the same thing. And what they got were the blue lines. And if you can't see the blue lines, it's because they're right behind the red lines. They are very good fit to the halo mass functions obtained from simulations. So here we are. We have an analytical tool to compute the halo mass functions, the outcome of this nonlinear process, without having to run a damn simulation. It's all nice and well, these simulations, we have to run them. And then you have to hire an army of grad students to analyze them and run halo finders. And it takes forever. You want to compute a halo mass function with cosmology? A millisecond nowadays on your computer, you know the answer, puff. So this is great. Not only does extended projector theory allow you to compute accurate halo mass functions, it also allows you to compute this sort of conditional probability function. It says, given a halo of mass m at redshift z2, what is the probability that that mass was locked up in a progenitor of mass m1 at an earlier redshift z1? And that is the key ingredient that you need to build halo merger trees. Right? So here's a pictorial view of that. In reality, what happens is you have some bunch of halos and they merge together and make bigger and bigger halo. That's a hierarchical structure formation. And when a halo accretes a smaller halo, that smaller halo now becomes a sub-halo of the bigger halo. And these sub-halos themselves can have sub-halos, and you have sub-halos and all blah, blah, blah. So you see that the hierarchical formation of halos gives rise to a hierarchy of substructure within halos. But what we can do now is we can go to a halo at redshift 0, say, and compute the probability. What is the probability that at some earlier redshift, it was in a progenitor of mass m1? And you can draw from that probability function. And now you can draw a realization of one of these halo merger trees. Okay. Now, does that work? Does it compare properly against simulations? Yes, it does. Before I show you that, here's just some nomenclature. If you go to this halo and you go look at the progenitors and you pick of those progenitors the most massive one, you click the most massive progenitor, you ask of its progenitors which one is the most massive one, and you keep going back and back and back. That is the history of the most massive progenitor. It's also known as the main progenitor history, or the mass assembly history, or the mass accretion history, or the MAH. It basically describes how does a halo build up its mass over time. Okay. And it's a powerful tool. And you can compute that. And here are the results. So on the left are results from a numerical simulation, a Bosch simulation. And what I did there is I went into the simulation, find halos of a given mass, say 10 to the 11 solar mass at redshift 0, and go to earlier snapshots of the simulation and ask what is the mass of its main progenitor. Okay, and trace it back. And then I have 1,000 halos, and I average that over all these 1,000 halos. And then I get the average mass assembly history. And that is what is plotted here. Okay, so in blue is for a halo of 10 to the 11 solar masses. And if you go to a more redder color, you go to more massive halos. So the first thing you notice, if you go to more massive halos, they assemble their mass later. That's a key prediction. Keep that in mind. More massive halos assemble later. Okay, we'll come back to that several times. And then you notice that if you go to low, more massive halos, the curve gets a little bit more wiggly. Why is that? Well, it's because I'm averaging over all the halos in the simulation. And by the time I get to these very massive ones, I only have a handful of them. There's only 5 of those halos in my big simulation box. So I get a noisy average, right? And then if I'm plotting here, I'm plotting the same thing, except now I'm plotting the log of this number as function of log of 1 plus z, which better shows what happens early on. It's all crammed here in this part. And what you see is at some point there's dotted lines because I can't get it anymore from my simulation. Because if I go to a 10 to the 11 solar mass halo and I ask, at 10 to the minus 1, that means I have 10 to the 10 solar masses. That's 10 particles in your simulation. You can't resolve this thing anymore. So your simulation has finite resolution, and that's sort of what you see happening here. But now you go to pressure sector theory, and you do this thing analytically. You make 10,000 realizations for a given halo mass of the mass accretion history, and you compute the average. And that's what is shown here. And if you would plot them on top of each other, the agreement is superb. So you don't need simulations, people. You can do this all analytically in no time. And I don't have any problems with wiggly lines because I don't have enough halos. I can make 10,000 massive halos if I want, no problem. And I don't have problems with resolution effects or anything. Okay? So this was the power. We became able to describe not only the linear structure formation, but all of nonlinear structure formation, how the halos, how many halos, how they grow over time. All of that we can do analytically. Okay? And remember, more massive halos form later. How am I doing on time? Okay, so what do these halos look like? Well, they look like NFW profiles. You may have heard of that. Turns out that these halos all have the same density profile. R to the minus 1 in the center, R to the minus 3 in the outskirts. This was Navarro, Frank, and White who first shown this. All dark matter halos, same density profile. Here's the analytical function. Okay, RS is the scale radius. That's where you have the transition, and the ratio between the virial radius, or the extent of the halo, and the scale radius is known as the halo concentration parameter. If you want to look at the circular velocity curve of one of those halos, okay, it rises, it has a maximum, and then it comes down. That maximum, you can show, happens at about 2 times the scale radius. And Vmax is defined as the circular velocity at that maximum. Okay? Sometimes people quantify halos by Vmax. That's what Vmax is. Now, remember that Vmax is a function of both the halo mass and the concentration. This will become more important tomorrow. Okay? So a halo of a given mass is more concentrated, will have a higher Vmax. Okay? All right. Next thing that we found in the simulations was that the concentration of a halo depends on halo mass. And typically, if you look at redshift 0 here, look at the black lines, which are the simulation results, what you find is that less massive halos are more centrally concentrated. And why would that be? Well, we actually think we understand that as well, because I just told you less massive halos assemble earlier. Earlier means when the universe was denser. So the halos ends up being a little bit denser, ends up being a little more concentrated. That simple idea allowed us to develop analytical models for what the halo mass concentration should be as function of halo mass and cosmology and redshift. And here these lines are such a model, and they fit the simulation result. So not only do we know how halos assemble, we also know what they're going to look like. You don't need a simulation. You just NFW halo with a concentration parameter, and we know what it is. And it's related to its assembly history. Now, the final thing, and then we're going to break for coffee, is halo bias. There's this one weird thing. Dark matter halos are made out of dark matter particles, yet they are a biased tracer of the dark matter density field. You think about that for a second. What? Dark matter halos are made out of dark matter, they are biased tracer of the dark matter density field. Sounds weird, but it's logical if you take into account that dark matter halos don't form at random locations in the universe. They form wherever the density field is overdense. It needs to be above that critical value of 0.686. So the idea is very similar with snowfall on Earth. I wrote down a statement and then I realized that's nonsense. Snowfall occurs at high altitudes. That's what I learned. Okay, but apparently here in Michigan that's violated. That proved. But forget that. Okay, snowfall occurs at high altitudes above the snow line. Snow line here. So if you actually look from Earth and you look at from space and you look at Earth and you look at where's the snow, it's highly clustered. Those clusters are called the Alps and the Himalayas and the Andes and the Rockies. Right? And why is that? Because it is above a given range, and it's the modulation of the Earth's surface that causes that to pick out a highly clustered distribution. And it's the same thing with the halos. Right? Here, these halos form together. There's a bunch of halos here and nothing here because underneath these small fluctuations are these large-scale modulations. That's what does it. We know everything we need to know about that density field statistically, so we can actually calculate what that bias is of dark matter halos. Okay, and here it is, so you can quantify the correlation function. You can go to your simulation, find halos of a given mass, and measure the two-point correlation function. Okay, I just told you how to do that. You just count pairs. And you can do the same thing, and you can do it for the dark matter particles, not the dark matter halos, but dark matter particles. That's your matter-matter correlation function, which is just the Fourier transform of the matter power spectrum. And it turns out that the halos are not the same as the matter-matter power spectrum correlation function. They are boosted by a bias parameter, B of M, which is just defined as by this equation. Okay, so B of M is just given by this expression, the ratio between the halo-halo correlation function and the matter-matter correlation function. So you can go into your simulation and measure that. B is function of M, and what you find, and this, I put an exclamation mark, this is very important. If you didn't know this already, print this in your head. What we find in the simulations is more massive halos are more strongly clustered. Okay, let it sink in. Now, not only that, we can calculate that bias, that halo mass dependence analytically. So even for describing the clustering of the halos. So we know what they look like, we know how they assemble, we know how many there are, we can calculate that, and we even can calculate how they are clustered in a statistical sense, because we can calculate that halo bias function. That was first done by Cole and Kaiser, and then more detailed work by Moe and White. And if you're interested in this stuff, there's a fantastic review paper by Vincent de Jacques on everything you want to know about halo bias. All right. So this was my primer on structure formation. Okay, it was going very fast, but if you want to know more, I highly recommend my video lectures on for a class that I teach at Yale on this stuff in much more detail. You can also look at this fantastic textbook, or Dragan, pay attention. Or this one. Okay, free advertisement. Brand new textbook on cosmology by Dragan. Okay, you can find all this information in more details there. So I suggest we break here for about 10 minutes. Yes, one question.
Well, is it possible that strong correlation between overdensities break ergodic principle at some point as defined in the previous slide? This is earlier in the slide.
If the strong correlations, well, the ergodic principle only holds on large scales, right? So very large scales. So it's not true that, of course, the density fluctuations here and next to it are not correlated. They are correlated. So you wonder, the idea that the ergodic principle holds is on very large scales, on scales where the correlation function becomes zero again. So I hope that sort of explains this. So it's sort of an idea. It's not very important for anything that follows the ergodic principle, but it's just sort of saying we can think of an ensemble average as a spatial average, and I hope I answered that question.
Second question on Zoom: halo bias, is halo bias the same as galaxy bias?
No, it's not. But galaxy bias is an outcome of halo bias, because galaxies live in halos. And once we quantify how galaxies live in halos, that's halo Cartesian modeling, then we can calculate the galaxy bias from the halo bias. So that's exactly what we're going to talk about later today. Okay, so let's break for 10 minutes, roughly. That's not even English. All right.
You have your own book. Did I tell you that they have like 10 copies of your book in the MPA library and they're all checked out? So that might be
all checked out
there. Yeah, checked out also, yes.
Hi. Nice to meet you.
I was at your talk at MIT earlier this year. It was lovely. I was excited.
I remember your face, yeah.
I have a quick question on the halo bias. So I'm a bit confused when you're like making this distinction between
to go and talk about the galaxy halo connection. I've been talking about that, right? The galaxy halo connection. Okay. So everything I'm going to say and what follows is based on two key premises. One is galaxies form and reside in dark matter halos. Okay. So I told you about how the halos form, and the idea is that there is some baryons, unfortunately, in the universe, and at some point they are going to cool and they're going to condense in the centers of these halos and make galaxies. And the idea is that all galaxies that we know of live in halos or subhalos. Those that live in the subhalos we call satellite galaxies, and those that live in the centers of the halos we call central galaxies. So that's not entirely true. There are a few galaxies that are not associated with halos. They're called tidal dwarfs. Not important. They are very, very few. The second premise is there exists some property or some properties of the galaxies that are tightly correlated with some properties of the dark matter halos in which they reside. Okay. To first order, probably bigger halos contain bigger galaxies. Right? Those are two premises. Keep them in mind moving forward. All right. So the galaxy halo connection, the idea is what we want to do there is say, I want to try and constrain the conditional probability function Pg given H. H is a set of halo properties. It can be things like halo mass, the spin parameter or angular momentum of the halo, the size of the halo, the triaxial shape of the halo, the concentration parameter of the halo, you name it. What is the probability that a halo with such properties contains a galaxy with properties G, which can be anything like luminosity, size, Boltzmann disk ratio, color, star formation rate, whatever. Okay? We would like to constrain that conditional probability function. Why? Because that galaxy halo connection characterizes the effective outcome of the galaxy formation process. And let me tell you one thing, galaxy formation is a complicated process. It's really complicated. Okay? It involves physics that covers many, many orders of magnitude in scale, time scales, spatial scales. It's extremely difficult. So if we can figure out what this relation is, bless you, then we have an effective description of the outcome of galaxy formation. This galaxy halo connection also links what we can see, aka galaxies, to what actually governs the dynamics of the universe, which is the matter, the dark matter mostly, because that's most of the matter. Okay? And finally, whenever you want to use galaxies as sort of tracers of the density field to do cosmology, and that's what we're interested in this room, this galaxy halo connection comes into play. You have to understand the galaxy halo connection to translate between these galaxies, these tracer particles, and the matter field. So that's why we're interested. Now, how can you constrain the galaxy halo connection? And this is a plot that sort of shows different methods that people use to get to the galaxy halo connection. On the x-axis, I go from being more data-driven to being more physics-driven. And on the y-axis, I go with increasing complexity, which is basically inversely proportional to speed with which I can do things. And sort of the summum of all things is just go and do a hydro simulation. Okay? So you assume that you know all the physics that is relevant for galaxy formation. You run your hydrodynamical simulation with the dark matter and the baryons in there, and you just run it. Okay? We know basically all the physics is relevant, but the problem is we can't resolve all the necessary physical skills. So what we end up doing is say at a given mass resolution element of my simulation, I don't know what goes on there. There's a million stars inside that little volume, and they're doing all sort of stuff. And I'm just going to describe the effective outcome of that as saying, oh, there's a certain amount of energy coming out from supernova, and that's going to do some stuff. And that's my subgrid model. Okay? Every of these simulations uses a subgrid model to describe what happens sub-resolution. And that's the tricky part. That's why two simulations never agree with each other, because everyone uses a slightly different subgrid physics model. But in principle, this hydrodynamical simulation, if you would have the correct subgrid physics described, should get you everything you wanted to know about the galaxy distribution. Okay? You can just run the simulation forward and then go into the halos, find the halos and look what galaxies are in them and quantify the galaxy halo connection. It's a way to do it. It's a very expensive one. These simulations take forever, and then someone else runs on the simulation, same thing, and they get a different answer. Okay. Well, you can do a little bit faster by using semi-analytical models. Back up. Semi-analytical models, SAMs. Semi-analytical models do the same thing, except that they don't use simulations. They say, well, I just told you, we know how the halos assemble over time. We just make these merger histories analytically, and then we put a recipe in that says, in a given halo at a given redshift, this is the rate at which the gas cools, at which the gas turns into stars, and how the stars then put back energy back into the intergalactic medium. And you just run this forward through your merger tree and make predictions for what the galaxies look like. Okay. It's less sophisticated than a hydrodynamical simulation, but basically you use the same sort of subgrid fit to describe a lot of stuff with simple recipes. It's much faster, but still pretty darn slow if you want to do this for many, many different cosmologies. The next thing up is empirical models, which is sort of a dumbed down version of a semi-analytical model, in which you say, I'm not really want to describe the actual star formation and feedback processes and the cooling recipes. I'm going to say, whenever my halo doubles its mass, by how much does the mass of the stars increase? You just quantify that. You say, okay, if m dot of the halo is a certain value, what is the corresponding m dot of the stars? And you quantify that by some function that has sufficient freedom, and you run it bram, bang through your merger trees, and you can make predictions for what your galaxies look like. Okay, and this is empirical modeling. It's become very popular recently. If you have heard of the universe machine by Peter Baruzzi, or the model Emerge by Ben Moster, that's basically what they do. It's very fast, and they can fit a large amount of data. Very powerful. You keep going to simpler, more simple models, you end up at some point at subhalo abundance matching, which is a sham subhalo abundance matching. What does it do? Well, basically you say, I'm going to go back to a simulation. I'm going to run a dark matter only simulation. I'm going to find and rank order my halos by mass. And I'm going to go to my data, a big survey, like Sloan survey, and I rank order all my galaxies in Sloan by stellar mass. And I'm basically going to assume that the most massive halo contains the brightest galaxy. And that's how I link my halo properties to galaxy properties. Super simple idea. And we'll see it does amazingly well. Okay? There's a few more things that I need to tell you about the method, but we'll come to that. And then finally, we come to HOD and CLF, which is halo occupation distribution and conditional luminosity function. And what you do there is say, remember the PG, that conditional probability function. Let's assume a functional form for that. Let's assume it's sufficiently general, has a number of free parameters, and I'm going to try and constrain these free parameters by just fitting directly to data. And that's what we're going to talk about today. Basically, what you're going to do there is you say, I'm going to assume a functional form for this HOD or CLF. I'm going to take halos, I'm going to populate them with galaxies according to that prescription, and then predict what the clustering of galaxies look like and compare it to data. Okay, so we will walk through that in a minute. Basically, along this scale, basically what you do is you go from an idea here where you say, I think I know what the galaxy formation physics is, I'm making an assumption about that, and I'm going to predict what the galaxy halo connection is. Okay. And here what we're doing is we're going to quantify the galaxy halo connection, try to constrain it with data directly in the hope that that way I can learn something about the galaxy formation physics. Okay. Now, another way to sort of split this up is to say, well, here, what I'm actually trying to do typically is to learn about galaxy formation. Okay, people who work in galaxy formation often run hydrodynamical simulations. But we're doing cosmology here. We don't care about damn galaxy formation, stupid things. We want to marginalize over it. We don't know how galaxies form, it's complex. So what we want to do is we want to marginalize over all our ignorance about the galaxy formation process. That's what we want to do. So we want to have a very quick way, very fast. We can do many different cosmologies and just try to marginalize over all this galaxy formation physics and see, can we discriminate one cosmology over the other? And that's where these two methods here come into play as sort of more powerful. Now, I wrote here not particularly useful for cosmology. I wrote yet there because efforts are underway to make also that component fast enough that we can actually do this. Okay, and more talks this week will show you how you can actually do that. Anyways, so here's the idea. We're going to start with data. We're going to start with a galaxy survey. DES, Sloan, whatever. From these surveys, you can construct summary statistics, like the clustering, the two-point correlation function of galaxies, or you can compute galaxy-galaxy lensing. We'll talk about that. Or satellite kinematics. You can get all sorts of summary statistics from the survey. And the idea is that we're going to use these summary statistics to constrain this galaxy halo connection. Okay, and we're going to see whether we can learn something about cosmology from that approach. Okay, and ultimately it ties into galaxy formation, but we're not going to do anything with that. Now, I told you about all these different galaxy properties that we would like to include in this, and all the different halo properties that we would like to include in this. That's hard. So let's start simple. Let's start and say, well, let's start with halo properties being halo mass. And for galaxy properties, it's the stellar mass or the luminosity. Now, I'm an astronomer. I know there's not the same thing to talk about stellar mass and luminosity. Okay, but for all practical purposes, it's the same. Right? It's just how many stars there are. Okay, so for this talk and this talk only, stellar mass and luminosity are the same thing. Right. So we're going to simplify things. We're going to basically ask, we want to constrain the probability, given a halo of a given mass m, what is the probability that it hosts a galaxy of luminosity L? That's what we want to know. Okay. Which brings me to the halo model, apparently. So this entire field started early 2000s. Okay. We knew we had these simulations and we had learned a lot from these simulations, and we had basically reached a point where we were able to analytically compute the halo mass function. How many halos are there? We knew what these halos look like. I should have pointed out when I said NFW profile, that's assuming cold dark matter. Okay. I'm working, unless I state otherwise, I'm assuming lambda CDM. Right? Of course, if you have self-interacting dark matter, you no longer have NFW halos. But we know how to compute the clustering of the halos, the halo bias function. And we can calculate the linear power spectrum. And it turns out that these are the 4 ingredients that you need to analytically compute the nonlinear matter power spectrum. This stuff that we were unable to do, and that's why we needed these damn simulations to start with. But when you have all these ingredients, you can actually compute the nonlinear matter power spectrum on the fly for any cosmology, boom, bam, no simulation needed. How do you do that? Well, I'm not going to go into the details, just very briefly. Remember that the power spectrum is a Fourier transform of the two-point correlation function. Two-point correlation function describes the number of pairs of particles. Okay. Now, 2 dark matter particles can either be in the same halo, in which case that pair contributes to what we call the 1 halo term of the power spectrum, or the 2 dark matter particles can be in 2 different halos, in which case that pair contributes to the 2 halo term of the power spectrum. Okay. We're going to assume that halos are spherical. They're not. It makes things easier. Okay. We're going to write the density profile of a halo as its mass times a normalized density profile. That's just easy mathematically. The normalized density profile is normalized such that if we integrate it over all space, it's unity. Okay. So we just take the mass out. And the Fourier transform of that thing is just given by the Fourier transform of u of x, and it's called u tilde of k. But I don't think we actually need that. I don't know why I wrote that down. Anyway, the whole point is, with these ingredients that I just told you, you do some algebra. Okay? And if you want to know the details, I'll make the lecture notes available, and in the end there's some extra lecture notes that you can read through, okay, where I show the step-by-step derivation. You can go to the video of lecture 13 of my ASTRO course. There's 2 papers here. Correa and Shed is an excellent review paper on the halo model if you're interested in this stuff. Okay. But the upshot is, here it is. This is the nonlinear matter power spectrum, okay, which has a 1 halo term and a 2 halo term. The 1 halo term is just given by basically the halo mass function and this density profile of a halo squared, because you want to compute pairs of particles, basically, right? So, and basically, if you want to compute the number of pairs of particles, you have to convolve the density profile with itself. In Fourier space, convolution is a multiplication. So that's why I get a square here of the Fourier transform of the density function, of the density profile. Right? So this is the 1 halo term, and the 2 halo term, okay, has the halo bias in, how are the halos clustered with respect to each other, and the profile of the halo mass function, and the linear power spectrum. So you see that with these 4 ingredients that we know how to compute analytically, we can now compute the nonlinear matter power spectrum. And if you do the Fourier transform of that, you get the nonlinear matter-matter correlation function. So even for this stuff, no simulations seem to be needed. How well does it work? Well, pretty darn well. So here is a power spectrum. This is actually what we call the dimensionless power spectrum. This is very often done. People just multiply pk by k to the third. That way it becomes dimensionless. Okay, so that's delta k here. So this is the linear power spectrum. Okay, it has that break. Okay? It doesn't turn down, but that's because I have multiplied by k to the 3. So basically, right, that's what you're looking at now. And here in black, everything is black, Frank. A solid line is the nonlinear matter power spectrum from a simulation. And you see on large scales is the same because there you're still in the linear regime, but on small scales, as I indicated, you get boosted power. Okay, because of all this stuff collapsing. And now you can compute the 2 halo term and the 1 halo term. Here's a 1 halo term, here's a 2 halo term, and this total is given by the dashed line. And you see here it is a very darn good fit to the nonlinear matter power spectrum. So, upshot, what you want to remember is we have all the tools in place to analytically compute the nonlinear matter power spectrum. Stop running simulations. Waste of time, heats the Earth's atmosphere, not good. All right. So now we'll take the next step. We'll look at that equation here for the 1 halo and 2 halo term, describing the nonlinear matter power spectrum, describes how the dark matter particles are clustered in space. And we're going to realize, hold on, if all galaxies live in dark matter halos, which was our premise, then I should be able to also compute the correlation function of the galaxies. All I got to do is replace basically m divided by the density. This is m is sort of the number of dark matter particles in my halo divided by the density of the dark matter. If I replace that by the number of galaxies in a halo of mass m, okay, so this is the average number of galaxies that live in a halo of mass m divided by the number density of galaxies, then rather than talking about particles that are dark matter particles, I'm talking about particles that are galaxies. And everything else is the same. And here, m squared here, that's basically because we're talking about the pairs of particles. Okay? So I need to just know the second moment. I need to know how many pairs of galaxies are there. Well, that's a half times n minus 1. That's the number of pairs of galaxies in a halo. And if instead of having this is the Fourier transform of how is the dark matter of the density profile of my Fourier, of my NFW profile. If I know how my galaxies are distributed in the halo, and I take a Fourier transform of that, okay, then I just replace UK by U galaxy. And I now have basically a recipe to compute the power spectrum of the galaxy distribution. So the upshot is the same formalism, the same mathematics can be used. All I need is now a model that describes how many galaxies are there on average in a given halo, and how are those galaxies distributed in that halo. And if I know that, I can compute the power of the galaxy correlation function, which is actually observable. Right? So, to summarize, what we need then is a halo occupation model. We have to first realize that in a halo, you can have multiple galaxies, right? Think of clusters of galaxies. There's always one that's special, that's the central galaxy, that's the one that lives right at the center. Okay? In the Milky Way, that's us, the Milky Way. And then there's a bunch of satellite galaxies, like the LMC and the SMC and 4NX, all these other little thingies. Satellite galaxies. We believe that those live in dark matter subhalos. Okay? So they're moving around in the host halo, they live in subhalos, and they're moving around. So if I want to quantify the halo occupation statistics, I need to first, how many central galaxies do I have on average in a halo of mass m? Well, I can either have 0 or 1, not more. So the average should be summing over the probability function to have n centrals in a given halo mass. That can only be 0 or 1. Okay, so the expectation value is just the same as this probability function. So I need to specify what is the probability that a halo of mass m has n centrals. Okay, so we'll specify that later on. And we need to know how are they distributed in the halo. Well, that's simple. They're all the center. So that's a delta function at the center. For the satellites, well, I need to know how many satellites are there. It's the same thing. Except that now I can have 0 satellites, and I can have as many as, well, infinite is probably exaggerated, but many satellites. Okay? And I just need to specify the probability function. What is the probability that a halo of mass m hosts ns satellites? Actually, I need to know more than that. I need to know how many pairs of satellites I have, because I'm going to do two-point statistics. We're going to do correlation function. Well, the pairs, for that, I need to know the second moment of that distribution. But the second moment of that distribution is, again, the same thing. I just need to put an n squared here. But all I need to know in the end is just that probability function. Okay. And I need to specify how the satellites are distributed in my halo. Those are the three ingredients I need. And puff, I compute a galaxy-galaxy correlation function. Okay. So that's just summarizing here the same thing. These are the three ingredients that we need to come up with. And then we have a recipe to compute a galaxy-galaxy power spectrum or correlation function. They're the same thing. One is a Fourier transform. And we can compare it to observations. Okay. Now, what do people typically assume for functional forms for this? A very popular model is the halo occupation distribution, or HOD. And HOD basically says, well, first of all, where does this come from? This basically comes from simulations. People had hydrodynamical simulations of galaxy formation. And there you can sort of see, you can just go to your halos and measure how many galaxies do I have as a function of halo mass. What does this simulation predict? Okay, and we can use that as guidance. And here's an example from a simulation. It's plotting the number of galaxies as a function of halo mass in an SPH simulation. And you sort of see the solid line here. If you look at the centrals first, well, it's either 0 or 1, and you see there's a transition. Puff. And it basically means in halos below this mass, you can't resolve the physics, or basically what really happens is you're talking about galaxies above a given luminosity. Okay? So the HOD always describes a luminosity threshold sample. It describes galaxies brighter than a certain limit. So when n, that n is the number of galaxies brighter than a certain limit. Well, there is going to be a halo mass below which galaxies of that brightness simply cannot form. Okay? You need to have enough baryons available to make enough stars to make such a bright galaxy. So n is going to be 0 below a given mass scale. And then there comes a mass scale where basically you do have enough baryons to make a galaxy that bright, and you transition to 1. But that transition is not a direct step function. Okay, there's a little bit of scatter, there's a little bit of stochasticity in galaxy formation. Okay? So that's why you get a sort of slow transition, which is actually described by an error function. Okay, and the error function has the characteristic mass. That's sort of the minimum mass, halo mass you need to get a galaxy of that luminosity. And it's specified by a scatter here, sigma log m, which describes how steep the transition is. Okay, if sigma L log m would be 0, that means there would be a direct step function. Okay? That would basically mean that galaxy formation is almost deterministic. In reality, we don't think galaxy formation is deterministic. It doesn't just depend on halo mass, there's some more stuff in it. So there's some scatter. That's what sigma log m describes. And then if you look at the satellites here, it sort of looks like a power law. So let's assume it's a power law. It has a power law slope alpha. It has a normalization m1. And typically we sort of cut it off here because we don't want to have this thing extend all the way down here. So we sort of have a cutoff mass. And it's sort of 5 parameters. So here I have a model that describes the occupation statistics of halos with 5 parameters. Okay. And this is a very popular model. My favorite model, though, is the conditional luminosity function. It's a little bit more sophisticated. It's not asking how many galaxies do I have in a halo. It asks something more specific. It asks how many galaxies do I have in a given halo of a given luminosity. Okay, so it's given by phi Lm. So it's given a halo mass m. How many galaxies on average of luminosity L do I have in such a halo? And typically, well, first look at this equation. So if you take the conditional luminosity function, and you integrate it over all halo masses, multiplied by the halo mass function, you get the galaxy luminosity function, right? So this says how many halos of mass m do I have per co-moving volume in the universe. This tells me how many galaxy luminosity L does each of those halos host on average. If I integrate that over all halo masses, I get the average number of galaxies of a luminosity L per co-moving volume. That's called the luminosity function. That's an observable. We can measure this. We have measured it. This, we know how to calculate for a given cosmology. Okay? So you can see that the conditional luminosity function links these two things together. You can integrate it over luminosity weighted by the luminosity of each galaxy. That predicts now how much light on average is coming from a halo of mass m. So you see that statistically, the conditional luminosity function describes the link between light, what we can see, and matter. And finally, it's directly related to these halo occupation models that I showed before, the HOD. You can just integrate it from luminosity L1 to infinity, and that's the same as the N that people use in these HOD models. Okay. So the upshot is there's different techniques that people use, and here's what we saw typically, what most people use for the conditional luminosity function. You split it again in the central part and the satellite part. And for the central part, we assume a log normal distribution. So here's a pictorial view. So this is the conditional luminosity function, luminosity for a given halo mass. We assume that the centrals, if you look at all halos of a given mass, they don't all have centrals of exactly the same luminosity. There's going to be some scatter. And we assume that that's a log normal. Okay, so there's a characteristic luminosity and some scatter in it. And what about the satellites? Well, we assume that the satellites have sort of a Schechter function. It has a slope, and then it turns over, because typically the satellites are going to be fainter than the central. Okay, so it turns over at some point. And that's quantified according to the Schechter function, right? So it's a power law, an exponential cutoff, and a normalization. Now, each of these parameters here are not parameters, they're actually functions of halo mass. So if I want to quantify the conditional luminosity function, I need to specify how all these parameters depend on halo mass. And that we typically do with about of order 10 free parameters. So unlike the HOD, which had only 5 free parameters, here I need 10 free parameters of order. But the HOD only describes one luminosity threshold sample. Okay, all galaxies brighter than, say, 10 to the 9 solar luminosities. If you want to also describe how many galaxies are there brighter than 10 to the 10 or 10 to the 11, then for each of those, you need an additional 5 free parameters. Okay? So if you want to break up your sample in 10 luminosity bins, you need 50 free parameters here with the HOD and only 10 for this one. So this one is much more convenient. It quantifies all the luminosities of the galaxies in addition to just how many are. Anyway, other than that, they're basically the same thing. Just this is coming from a galaxy group catalog. What some people have done is they have devised schemes in which you can group galaxies together in a redshift survey. Okay, and then you assign a halo mass to it. I don't have time to go into how you do that. The upshot is now you can take all your groups of a given halo mass, say in this mass range here, and you look at the luminosities of all the galaxies in all those groups of that mass. That is basically the conditional luminosity function. Okay, and if you do that for different group masses, you can sort of see that this functional form that I assumed with a log normal and a Schechter power function is not a stupid assumption, because it exactly perfectly fits the data that we get from galaxy group catalogs. Okay, so just to give you some motivation for why we picked that functional form. All right. So the final thing that I now need to quantify my halo occupation statistics completely is the HOD and the CLF just tell you how many galaxies there are, but I need to know how many pairs of galaxies there are of satellites, right? Because I need to compute the 2-point correlation function. Well, the number of pairs, okay, is just given by this expression, and it's ultimately just related to I need to know a probability function for n. And what you can do is you can write the number of pairs as some function times the first moment squared, ns squared. Okay, now let's see. Right. What we typically do, what almost everyone does, is they assume that the functional form for the number of satellites is a Poisson distribution. And the cool thing about a Poisson distribution is if you specify its first moment, you know everything you need to know. It's completely specified with the first moment only. Okay. In particular, for a Poisson distribution, this thing, the number of pairs, is exactly equal to just ns squared. Okay? In other words, beta is 1. So what I'm trying to say is most people assume that the number of satellites obey Poisson statistics. Is that reasonable or not? We'll come back to that in a minute. And if they assume Poisson statistics, basically what they're saying is beta is 1. It means the number of pairs is just the first moment squared. And I'm done. Okay? Now, let's see. What is next? The next thing we need to know is how are those satellite galaxies distributed in the halo? You know, it's what is the radial number density profile of the satellites? Most people just say, well, let's assume they just follow also an NFW profile. But you can be a little bit more general and say, well, there's no good reason why they should. The let's assume they have a more generic functional form. So I'm introducing here a free parameter, gamma, which is the central cusp slope. Okay. And I'm introducing a calligraphic R here in front of RS. RS is the scale radius of the dark matter halo. Okay. What is the radial profile of the satellites? Well, it has a characteristic radius R times RS. And gamma is a free parameter. Now, if I set gamma and R both equal to 1, then this profile is just the actual NFW profile of the dark matter halo. In other words, if gamma and R are both equal to 1, what you're basically effectively assuming is that satellite galaxies are an unbiased tracer of the dark matter mass distribution within individual halos. Is that a reasonable approximation? It's one that many people make. Okay. If you're uncomfortable with that, well, here's a way to make it a little bit more flexible, to add more freedom to your model by just introducing 2 additional free parameters. But you can use anything you want. Ideally, we want to just marginalize over all these possibilities and ultimately constrain it with the data. So let's have a look. And I think then we're done for the day. When am I going to stop? Well, I'm almost there. So two more slides, I think. Good. So I told you that people typically assume Poisson statistics. Well, there's a way in which we can actually test this. You can go to the same group catalogs that I mentioned earlier, okay? And I've done here you go to different halo mass bins for the groups, and you plot the number of satellites in each of those groups. Those are the histograms, okay? So these are, look here, these are halos in a range of around 10 to the 14.1 to 10 to the 14.3 solar masses. And on average, you have about 12, 13 satellites, but there's some distribution around. Now, if it is a Poisson distribution, I can calculate analytically what that distribution function should be. All I need to know is what is the average N of S. So I take the average N of S here, and the solid line is a Poisson distribution with that average N. And you see that the histogram is in fairly good agreement with that solid line. So, hey, yes, indeed, satellite galaxies seem to obey roughly Poisson statistics. Is that physically logical? No, not really. Remember, where the satellite galaxies come from, they live in subhalos. And subhalos themselves have subhalos. They have subhalos. So typically when one of these things falls in, you don't just accrete one subhalo, because that subhalo itself will have subhalos. So you create a whole bunch of satellites together. And that's not a Poisson process. So you should be a little bit surprised that it seems to be so close to Poisson. And in general, if you're fully general, you say, I'm not going to just assume Poisson. And one way to do that is say, I'm going to put that beta back in and say, I'm not going to assume beta as 1. I'm going to assume beta as a free parameter. At least you now have more freedom in your model. Okay. But most people assume Poisson, and this is why. All right. The final thing, and then we're done, is the radial profile of the satellites. Well, we can go and measure it. In fact, people have done that all the time. People have looked at clusters for many years and just looked at the radial profile of satellite galaxies in clusters. This is from a very nice study by Lin, Moore, and Stanford, 2004. So the dots are actual measurements of the radial profile of satellite galaxies in clusters. The solid line is the best fit NFW profile. Well, that fits pretty darn good. This is one of the reasons why many people assume satellite galaxies follow an NFW profile. In other words, gamma and R are equal to 1. People have done similar sort of things with other surveys. With the Sloan survey, you go to isolated galaxies and you look at the radial profile of the faint satellites around them. In many cases, all the dots are data and the lines are NFW fits. NFW profile seems to fit the radial profile very, very nicely. Although I should point out, often the concentration that you have to assume is not necessarily equal to the concentration that you predict for halos of that mass. Okay, in other words, that calligraphic R that I mentioned does not have to be 1. Now, I want to end today on one surprising note. So here I show that data tells you the radial profile of satellite galaxies seems to be roughly NFW. I also told you that satellite galaxies live in subhalos. So the radial profile of subhalos should also be the same, right? Unfortunately, it's not. You can go to your simulation, find halos, and measure the radial profile of dark matter subhalos. And that is shown here. So this is radius, in units of virial radius, the number of subhalos, and this is data from simulations, these dots. These are the dark matter density profiles themselves. So if subhalos were unbiased traces of the dark matter particles in a halo, the subhalo should have the same profile as the dashed line. But they're much more centrally cored. They have a core in the center, not gamma to the 1, gamma 0. Here's a ratio between the two. Okay, so if subhalos were an unbiased tracer, they should be here. There seems to be a deficit of subhalos in the centers of these halos. Now, I've worked on this quite extensively, and I'm convinced that most of this is an outcome of artificial subhalo disruption. The simulations simply cannot resolve the dynamics properly, and these subhalos just are ripped apart, whereas they shouldn't be. If you would have better resolution, they would survive, which might explain why the satellite galaxies in the real universe have a profile that does look more like this. But it has important implications because, as Garrison will tell you, you can also just go to a numerical simulation and put galaxies on subhalos. And if you do that, you're automatically going to put your satellites on a profile that looks like this, which may not be consistent with the data. And people have realized that, and then they said, okay, then we have to add a bunch of galaxies extra to it. And that's often called orphan galaxies. Okay? And that means once you use a simulation and you put satellites on subhalos, you often have to add an extra model to it to describe these sort of missing subhalos. Okay? And that adds some extra degrees of freedom. And we'll talk more about that later tomorrow. And this is exactly where I want to stop today. So that's it. You want to do a little Q&A or?
One question from Zoom: how again are we defining halo concentration? There's there are quite a few different definitions, no?
The standard definition for halo concentration is it's the ratio of the virial radius of a halo, which is a slightly ill-defined quantity. That's probably where that question is going at, divided by the scale radius, which is a fairly well-defined quantity because that's basically where you go from an r to the -3 to an r to the -1. Okay. Now, what is the virial radius? Well, it's defined as a radius inside of which the universe, the halo, has a density that is some number times the background density of the universe. What is that number? Well, according to the spherical collapse model, you can calculate where you expect it to be, and then for lambda CDM cosmology, it's about 340. And then some people say, well, 340, let's pick 200. And then some people say, well, actually, if you calculate it, it should be 178, but that's for 9 to the city. So it's a mess, okay? And it's a disgrace for this field that 30 years of measuring halo profiles, we still don't have a freaking definition of what a halo is, okay? And it's a shame because I spend half my time converting from one halo mass definition to the other, and I'm sick and tired of it. But that's where we were going at. So it's a virial radius divided by the scale radius. How you define your virial radius, that depends on who you are, apparently, these days, which is very annoying. But yeah, sorry for venting my frustration.
There's a couple of questions here.
Hold on.
Okay, so you can tap the thing in front of you. It'll go from red to green, and then you can speak. You see on your table there should be a disc. Should be a disc around with a red. Yeah.
Okay. That is.
You don't have to come close to it. Just.
Oh,
just
okay, sure.
Don't need it.
Okay, so assuming that this now works, when you show the plot of the one halo and the two halo term, I mean, it went up to, let's say, K of 100 or 1,000. I mean, that's smaller than the size even of like a galaxy. So how do I interpret this plot? Or does it not have any physical meaning?
So this is just, you're absolutely right. So this is the nonlinear matter correlation function, PowerSpectrum, for the matter, not for galaxies.
Oh, okay. Sorry, I thought this was the okay.
Right. This is for the matter.
Okay.
So there you can define it all the way to
Yeah,
small
okay,
scales.
okay.
For galaxies, of course, you're right. At some point, they start to touch each other, and then also
Okay, sure.
there we can never measure it smaller scales than about 10 kiloparsec, and even that's pushing.
Okay. Okay, I misunderstood. Thank you.
All right.
You can tap that again, it'll turn back to red, and maybe let's take one more question there.
Thank you for your lecture. So my question is mainly from our observable universe. In cosmic web, if our galaxies located not in a cluster, but maybe in some part of filaments near void, and we can call these galaxies as isolated galaxies because they have a big distance to another galaxies.
Mhm.
Can we estimate the properties of dark halo around these very maybe small and not very active isolated galaxies in a filament?
So you're getting to a very thorny issue. You're saying, well, some halos live in filaments, some halos of the same mass live in voids, some halos of the same mass live next to an enormous cluster, big halo. We are assuming here that the occupation statistics and everything only depends on the mass of the halo. Maybe it actually depends on the environment in which that halo lives. God forbid us all if that's true. It is true. It's ignored. It's called assembly bias. It's what's going to ruin our afternoon tomorrow. So yeah.
Thank you.
Thank you. Maybe this is a good moment to, let's take a 10-15 minute break. There's coffee, should be some outside.